On a clear autumn night, far from city lights, you can see it with your naked eyes. A faint smudge of light against the darkness, soft, delicate, almost ghostly in its presence. The Andromeda Galaxy. 2.5 million light-years away, yet visible without telescopes, without instruments, just the ancient photons striking your retina after an unimaginable journey through space and time. We can see it. We can photograph it. We can measure its distance with precision, count its trillion stars, map its spiral arms. We know more about Andromeda than our ancestors knew about the next valley over. And yet, despite all our knowledge, all our technology, all our dreams of cosmic exploration, we will never reach it. Not in 100 years, not in 1,000, not ever. This is not pessimism. This is physics. And tonight, we will explore exactly why. The impossibility of reaching Andromeda is not a simple story of distance, though distance plays its part. It is a cascade of barriers, each one more profound than the last. There are the practical limitations, the engineering challenges of building a craft that could survive millions of years in the void. There are the energy requirements, so vast they make our current capabilities seem like striking a match in the darkness. There is the speed limit of reality itself, light speed, which even at its incomprehensible velocity is simply not fast enough. And then, stranger still, there are the cosmic forces working against us. Time itself begins to behave differently at extreme velocities. Space expands between galaxies faster than anything can cross it. The very fabric of the universe conspires, not with malice, but with indifference, to keep us isolated on our island of stars. Yet in this impossibility lies a profound beauty, a reminder that the universe is larger, older, and more mysterious than human ambition can overcome. That there are boundaries written not by our limitations, but by the fundamental laws that govern existence itself. Tonight, we will trace each layer of this impossible journey. We will calculate what it would take in fuel, in time, in human generations, to even attempt such a voyage. We will explore the physics that bends around extreme speeds, the emptiness between galaxies that makes interstellar space seem crowded by comparison. We will consider the theoretical escapes, wormholes and warp drives, the mathematical possibilities that may forever remain beyond our grasp. And we will confront the ultimate barrier, the accelerating expansion of space itself, driven by dark energy, slowly but inevitably pushing Andromeda further away with each passing moment. This is not just a story about a galaxy. It is a meditation on limits, on the scale of the cosmos, and on what it means to be a curious species trapped by the laws of physics on a single world, staring outward at wonders we can observe but never touch. Before we drift deeper into this cosmic contemplation, I want to ask you something. Wherever you are right now, listening to these words, whether you're settling in for sleep or simply letting your mind wander through the universe, leave a comment below. Tell me where you're watching from, what time it is in your corner of the world. There's something quietly beautiful about knowing that people all across this planet, scattered through time zones and cultures, are all looking up together, wondering about the same impossible distances. Now, let us begin. Let us look up at Andromeda together, that soft light in the autumn sky, and truly understand what we are seeing. Not just a galaxy, but a farewell letter written in starlight. A message from a place we will never visit, reminding us that some journeys exist only in contemplation, and that sometimes the most profound experiences are not about arrival, but about the awe of simply witnessing something beautiful, impossibly far away. On a clear, moonless night, far from the glow of city lights, you can see it. A faint smudge of light suspended in the constellation of Andromeda, delicate and distant, barely distinguishing itself from the darkness surrounding it. To the naked eye, it appears as nothing more than a whisper of luminescence, a ghostly patch that seems to hover between stars. Ancient astronomers noticed this peculiar glow. Persian astronomer Abd al-Rahman al-Sufi described it in the year 964 as a small cloud, marking it in his Book of Fixed Stars. For centuries, observers across cultures gazed upon this mysterious light, cataloguing it among the celestial curiosities that defied easy explanation. They had no idea what they were truly looking at. To ancient civilizations, this smudge was simply part of the heavens, perhaps a wisp of cosmic vapor, perhaps a distant congregation of stars too far to resolve individually. Chinese astronomers recorded it. Islamic scholars studied it. European astronomers eventually classified it alongside other fuzzy patches as a nebula, from the Latin word for cloud or mist. For generations, humanity looked upon Andromeda and saw merely a luminous fog, a decorative detail in the grand tapestry of the night sky. The truth would remain hidden for centuries more, waiting for telescopes powerful enough and minds bold enough to comprehend what these ancient observers could never have imagined. The revelation came in the early 20th century, and it shattered our understanding of the cosmos. In 1923, astronomer Edwin Hubble, using the massive 100-inch Hooker telescope at Mount Wilson Observatory, began studying this nebula with unprecedented clarity. Within its hazy glow, he identified something remarkable: individual stars. Among them, he found Cepheid variables, stars that pulse with a predictable rhythm, their brightness changing in cycles that betray their true luminosity. By measuring these pulses, Hubble could calculate distance with a precision previously impossible. The numbers were staggering. This was not a cloud of gas within our own galaxy. This was an entirely separate galaxy, an island universe containing hundreds of billions of stars, existing far beyond the boundaries of the Milky Way. In that moment, the universe expanded exponentially in human consciousness. What ancient astronomers had called a small cloud was actually a cosmic giant, a galactic twin to our own home, separated from us by a gulf so vast it defied all earthly measures of distance. Andromeda lies approximately 2.5 million light-years from Earth. To speak this number casually is to risk missing its profound weight. Let us unpack what this truly means. A light-year is the distance light travels in 1 year, moving at 186,282 miles per second, the fastest speed possible in our universe. In a single second, light could circle Earth's equator more than 7 times. In 1 year, light travels nearly 6 trillion miles. This is already beyond human comprehension, yet it represents merely the beginning of our journey to Andromeda. Multiply that single light year by 2.5 million. The result is a distance of approximately 15 quintillion miles. Written numerically, that is 15,000 miles. A number so large it ceases to have meaning in any context we experience daily. If we could drive to Andromeda at highway speeds of 60 miles per hour, never stopping, never slowing, the journey would take more than 28 billion years. The universe itself is only 13.8 billion years old. We could begin driving before the first stars ignited, and still not arrive before the present day. Even light, moving at the absolute cosmic speed limit, takes 2.5 million years to cross this void. The photons entering your eyes when you observe Andromeda began their journey long before humans walked upright, before our species existed in any recognizable form. When that light departed from Andromeda's stars, Earth was in the midst of the Pliocene epoch. Australopithecus, our distant ancestors, were just beginning to appear in Africa. Saber-toothed cats prowled ancient grasslands. Mastodons wandered forests that would one day vanish beneath ice ages not yet begun. This means something profound and unsettling. We are not seeing Andromeda as it exists now. We are seeing it as it was 2.5 million years ago, a ghost of the past frozen in light. The stars we observe may have already died, their light still travelling toward us, carrying the image of their existence long after they have collapsed into darkness. New stars have certainly been born in Andromeda since that light began its journey, stars we will not see for millennia to come. We are observers not of the present, but of deep time, looking backward across an abyss that separates not just space, but epochs. Within this ancient light lies a galaxy of almost incomprehensible scale. Current estimates suggest Andromeda contains approximately 1 trillion stars. 1 trillion. To understand this number, imagine attempting to count them. If you counted 1 star per second without pause, without rest, it would take you more than 31,000 years to count them all. The entire span of recorded human history would pass. Civilizations would rise and fall, and you would still be counting stars in Andromeda. Consider our own sun, a single star among hundreds of billions in the Milky Way. Around this one star orbits Earth, teeming with billions of humans, countless species of life, all our history, our art, our wars, our loves. Now multiply that single sun by 1 trillion. Each of those stars in Andromeda is a potential sun, possibly surrounded by planets, perhaps harboring worlds with their own oceans, atmospheres, maybe even life. The scale transcends imagination. If Andromeda's stars were grains of sand, they would fill not just a beach, but hundreds of beaches stretching across continents. The galaxy itself spans approximately 220,000 light-years from edge to edge, making it significantly larger than our own Milky Way. It is a spiral galaxy like ours, with elegant arms of stars sweeping outward from a central bulge, rotating slowly over hundreds of millions of years. From our perspective, we see it tilted, angled, so that we glimpse both its disk and its depth. If we could somehow compress time and watch Andromeda over eons, we would see it rotating like a cosmic pinwheel, stars sweeping through their orbits, entire stellar neighborhoods drifting through space in a grand celestial dance. What appears to our eyes as a small, faint smudge is actually one of the most massive structures visible in our night sky. If Andromeda were brighter, if our eyes could capture all its light, it would appear 6 times wider than the full moon, stretching across the heavens like a luminous highway. But most of its light is too faint for our limited vision to perceive, and so it remains hidden, a giant disguised as a ghost. This is the deceptive beauty of Andromeda. It appears gentle, distant, almost insignificant against the backdrop of stars. Yet it is a colossus, a gravitational titan containing more mass than 1 trillion suns, hurtling through space at 250,000 miles per hour toward our own galaxy. In approximately 4.5 billion years, Andromeda and the Milky Way will collide, merging into a single, larger galaxy that astronomers have already nicknamed Milkomeda. But that collision exists in a future so distant it is beyond relevance to anything we know or will ever know. For now, Andromeda remains suspended in the darkness, a monument to distance, a reminder that the universe operates on scales that dwarf human experience entirely. When we look upon that faint smudge of light, we are not simply seeing another galaxy. We are witnessing time itself, frozen in photons, delivering a message from an era when humanity did not yet exist. We are seeing light that has travelled longer than our entire evolutionary history, crossing a void so vast that no human technology, no conventional spacecraft, no amount of fuel or time could ever hope to traverse it. This is what we are actually looking at when we gaze upon Andromeda, not a nearby neighbour, but a distant monument to the impossible, beautiful beyond words, and unreachable beyond comprehension. We imagine light as the ultimate velocity, the cosmic speed that nothing can surpass. Yet when we turn our gaze toward Andromeda, even light itself becomes painfully slow. The universe has woven into its fabric a fundamental limit, a boundary so absolute that no amount of fuel, no technological breakthrough, no force in the known cosmos can breach it. This is not a limitation of engineering. This is a law written into the architecture of reality itself. Light travels at approximately 186,000 miles per second. In a single heartbeat, a photon crosses the distance from Earth to the Moon. In 8 minutes, sunlight reaches our planet after its journey from the solar surface. This speed seems incomprehensible by human standards. Our fastest jets, our most powerful rockets, they are glacial by comparison. Yet in the vast emptiness between galaxies, even light becomes a crawling thing. To reach Andromeda at the speed of light would take 2.5 million years. Let that settle into consciousness. Not 2.5 million seconds, or minutes, or days. 2.5 million years. If a beam of light departed Earth at the moment our earliest human ancestors first stood upright on the African plains, it would only just now be arriving at Andromeda's outer edges. Entire species have risen and fallen in the time it takes light to cross this single gap in space. Civilizations have emerged, flourished, and disappeared into archaeological mystery. The very shape of human evolution, from primitive tool use to quantum computers, represents a fraction of the time light requires for this journey. This is the speed limit of reality, and it is not fast enough. The cosmic speed limit exists because of the structure of space-time itself. According to Einstein's theory of relativity, space and time are not separate entities, but interwoven dimensions forming a unified fabric. As an object accelerates through space, something remarkable happens. Time begins to dilate. Mass begins to increase. These are not tricks of perception. They are measurable, physical transformations of reality. The faster you travel, the more your mass grows, and the more energy is required to accelerate further. At the speed of light, the mathematics become infinite. An object with mass would require infinite energy to reach light speed. It is not merely difficult, it is impossible, prohibited by the fundamental equations that govern existence. Only massless particles, photons of light itself, can travel at this ultimate velocity, and they do so because they have no choice. They are born moving at light speed and can never slow down, never rest, never pause. They are the universe's eternal wanderers, forever in motion. But we are not made of light. We are matter, bound by mass, and the speed limit applies to us with unforgiving precision. Consider our current capabilities. The Parker Solar Probe, launched in 2018, is the fastest human-made object ever created. At its peak velocity, it reaches approximately 430,000 miles per hour as it plunges through the Sun's outer atmosphere. This speed is staggering, unprecedented, a triumph of engineering. Yet compared to the speed of light, it is moving at less than 0.64% of light speed. At this velocity, reaching Andromeda would take approximately 3.9 billion years. The Earth itself will likely be consumed by the expanding Sun before such a journey could conclude. Voyager 1, humanity's most distant ambassador, travels through interstellar space at roughly 38,000 miles per hour. It is the farthest object we have ever sent from Earth, now beyond the heliosphere, drifting through the space between stars. Its journey is legendary, its achievements unparalleled. Yet at its current speed, Voyager 1 would require more than 73 billion years to reach Andromeda. The universe itself is only 13.8 billion years old. Voyager would need more than 5 times the current age of the cosmos to complete this single journey. These numbers are not meant to discourage, but to illuminate the true scale of what we face. The gap between our current technology and the requirements for intergalactic travel is not a gap measured in decades or centuries of development. It is a chasm measured in orders of magnitude, in fundamental transformations of physics itself. Why can't we simply keep accelerating? Why not build a spacecraft that continuously fires its engines, adding velocity year after year until we approach the speed of light? The answer lies in the nature of energy itself. As velocity increases, so does relativistic mass. The faster you go, the heavier you become from the perspective of the universe. This increasing mass demands exponentially more energy to achieve each additional increment of speed. Accelerating from 0 to 10% of light speed requires a certain amount of energy. Accelerating from 10% to 20% requires far more. By the time you approach 90% of light speed, the energy requirements become astronomical, exceeding the total output of entire stars. There is a curve, elegant and merciless, that describes this relationship. Near light speed, the energy required to gain even a fraction of additional velocity skyrockets toward infinity. The universe enforces its speed limit not through barriers or walls, but through mathematics. Every additional mile per hour becomes exponentially more expensive in energy until, at light speed itself, the cost becomes infinite. No conceivable power source could provide it. Not fusion, not antimatter, not the harnessed energy of collapsing stars. Some have theorized about photon drives, propulsion systems, that convert pure energy directly into thrust with perfect efficiency. Even these hypothetical engines, operating at the absolute limits of thermodynamic possibility, would struggle with the energy demands of near-light speed travel. The fuel requirements alone would dwarf the mass of the spacecraft many times over, creating a paradox where the ship becomes too heavy to accelerate efficiently, requiring yet more fuel, which adds more mass, which requires more energy. The speed of light is not merely a speed, it is a horizon, a boundary condition woven into the cosmos. To approach it is to approach a realm where time and space transform, where the familiar rules of motion dissolve into something stranger, more profound, and ultimately unreachable for objects with mass. Yet even if we could reach light speed, even if some breakthrough allowed us to circumvent the energy requirements to somehow achieve this ultimate velocity, we would still face an uncomfortable truth. It would not be enough. Andromeda would still lie 2.5 million years away. The observable universe, stretching 93 billion light-years across, would remain forever beyond reach. Galaxies billions of light-years distant would drift in isolation, untouchable, knowable only through the ancient light that reaches our telescopes after journeys longer than human comprehension. Light speed is simultaneously the fastest velocity possible and desperately, impossibly slow for the scale of the universe we inhabit. It is a cosmic irony, a reminder that the universe is built on principles that both enable and constrain. The same laws that allow stars to shine and galaxies to form also ensure that vast regions of space will remain forever separate. Islands of reality disconnected by distances too great for even light to bridge in any meaningful time frame. As we contemplate the journey to Andromeda, we must first reckon with this fundamental barrier. The speed limit is not a challenge to overcome. It is a feature of existence itself, as immutable as the passage of time, as certain as gravity. To travel between galaxies is not simply a matter of building faster ships. It requires confronting the deepest structures of physics, the very framework upon which reality is constructed. And that framework, elegant and beautiful as it may be, offers no easy passage to the stars beyond our own galactic home. We have seen the vastness of our own solar system, felt the years required to reach Saturn's rings, experienced the gravity of Jupiter bending space-time itself. But Andromeda lies not millions of miles away, but 2.5 million light-years distant. To reach it in anything resembling a human lifetime requires speeds that approach the speed of light itself. And here, in the cold mathematics of propulsion, we encounter a wall so fundamental that it reshapes our entire understanding of what is possible. This is not a challenge of engineering or patience. This is a confrontation with the finite energy of the universe itself. The fuel problem begins with a simple question. How much energy would it actually take to accelerate a spacecraft to relativistic speeds, to velocities measured as fractions of light itself? The answer is not merely large, it is incomprehensible, astronomical in a way that dwarfs even the distances we have been exploring. Consider a modest spacecraft, perhaps 1,000 kilograms in mass, roughly the weight of a small car. To accelerate this vessel to just 10%, the speed of light would require approximately 450 million billion joules of kinetic energy. To put this in perspective, this is roughly equivalent to the total energy released by 100 megatons of TNT, more than the most powerful nuclear weapon ever detonated by humanity. And this calculation assumes perfect efficiency, a 100% conversion of fuel into forward motion, something that no propulsion system has ever achieved or ever will achieve according to the laws of thermodynamics. But 10% of light speed is not nearly fast enough. At that velocity, the journey to Andromeda would still take 25 million years. To make the journey in something resembling a human timescale, we need to approach significant fractions of light speed, perhaps 90% or even 99%. And here, the energy requirements do not merely increase linearly. They explode exponentially, climbing toward infinity as we approach the cosmic speed limit. At 90%, the speed of light, that same 1,000 kilogram spacecraft would require kinetic energy equivalent to approximately 10 billion joules. This is more energy than the entire United States produces in multiple years. For a single small spacecraft, for a single journey. And we have not yet addressed the most devastating aspect of the fuel problem, the tyranny of the rocket equation. The rocket equation, formulated by Konstantin Tsiolkovsky over a century ago, describes a merciless truth about space travel. To carry fuel, you must accelerate that fuel. To accelerate more fuel, you need even more fuel to push it. This creates a cascading requirement where the mass of propellant needed grows exponentially with the desired change in velocity. For journeys within our solar system, this is manageable, barely. For interstellar travel at relativistic speeds, it becomes absurd. Calculations reveal that to accelerate even a small probe to half the speed of light using conventional rocket propulsion, the mass ratio, the ratio of fuel to payload, would need to exceed millions to one. This means that for every kilogram of spacecraft, you would need millions of kilograms of fuel. The spacecraft would be essentially invisible, a microscopic seed buried within a mountain of propellant. And this fuel itself would need to be accelerated, requiring even more fuel in a feedback loop that spirals toward mathematical impossibility. Perhaps we might imagine advanced propulsion systems could solve this. Nuclear fusion, the process that powers the stars themselves, releases far more energy per unit mass than chemical rockets. A fusion drive could theoretically achieve exhaust velocities measured in percentages of light speed, yet even fusion, for all its promise, falls dramatically short of what would be required for Andromeda. A spacecraft using deuterium-helium-3 fusion, one of the most efficient fusion reactions we can envision, might achieve exhaust velocities of perhaps 5% the speed of light under ideal conditions. Using the rocket equation, such a system would still require fuel-to-payload mass ratios in the thousands to reach even modest relativistic velocities. The engineering challenges multiply beyond comprehension. Where would this fuel come from? How would it be stored? How would the spacecraft survive the acceleration forces? How would it dissipate the waste heat generated by the fusion reactions, heat that could vaporize the vessel itself? Then there is the ultimate fuel source that physics allows, matter-antimatter annihilation. When matter and antimatter meet, they annihilate completely, converting 100% of their mass into pure energy according to Einstein's famous equation, E=mc2. This is the most efficient energy conversion possible in our universe, short of manipulating space-time itself. A single kilogram of antimatter annihilating with a kilogram of matter would release approximately 180 petajoules of energy, equivalent to the explosive force of 43 megatons of TNT. Even with this ultimate fuel, the numbers remain staggering. To accelerate our modest spacecraft to 90% light speed, accounting for the need to also decelerate at the destination, we would require thousands of kilograms of antimatter. This represents more antimatter than humanity has ever created by a factor of billions. In all of human history, across all particle accelerators on Earth, we have produced perhaps a few nanograms of antimatter, particles that exist for microseconds before annihilating. Producing kilograms would require energy expenditure equal to a significant fraction of humanity's total power generation for years or decades. And antimatter is not merely difficult to produce. It is nearly impossible to store. Antimatter annihilates instantly upon contact with normal matter, which means it must be suspended in electromagnetic fields, contained in perfect vacuum, isolated from every atom of the spacecraft carrying it. Any failure, any fluctuation in the containment system would result in catastrophic annihilation, a detonation that would make nuclear weapons seem gentle by comparison. Let us compare these requirements to human civilization's total energy capacity. Humanity currently generates approximately 580 exajoules of energy per year from all sources combined: fossil fuels, nuclear, renewables, everything. A single journey to Andromeda at high relativistic speeds, using even the most efficient propulsion systems we can imagine, would require energy measured in thousands or tens of thousands of exajoules. This is multiple years of Earth's entire energy output, devoted solely to accelerating one spacecraft. Not to build it, not to sustain it, not to power its systems, just to make it move. The mathematics are unforgiving. The physics offers no loopholes. Every additional unit of speed demands exponentially more energy. Every kilogram of payload multiplies the fuel requirement. The rocket equation does not negotiate. It does not bend. It simply calculates, and the calculations reveal that conventional propulsion, even propulsion using physics we understand and fuels we can theoretically create, cannot bridge the gulf to Andromeda. Here, in the sterile beauty of equations, we find not just an engineering challenge, but a fundamental barrier. The fuel problem is not a problem of insufficient technology or inadequate investment. It is a problem of available energy in a finite universe. To travel between galaxies using rockets, even perfect rockets burning perfect fuel, requires more energy than civilizations can reasonably harness. And so we are left with a profound realization. The distance to Andromeda is not measured only in light years. It is measured in energy we do not possess, fuel we cannot create, and physics that offers no compromise. The journey ahead demands that we look beyond conventional propulsion entirely, into realms where space-time itself might be manipulated, where the very fabric of reality could become our engine. But those possibilities come with their own impossible requirements, as we shall soon discover. As we contemplate the journey to Andromeda, accelerating to speeds that approach the ultimate cosmic limit, we encounter something far stranger than distance or fuel. We encounter time itself, no longer flowing like a steady river, but bending, stretching, and fragmenting into parallel streams that diverge with every increment of velocity. This is not science fiction. This is the reality described by Einstein's theory of relativity, a framework so thoroughly tested and confirmed that it governs the operation of GPS satellites orbiting Earth at this very moment. At relativistic speeds, speeds approaching the velocity of light, time becomes fluid. It dilates, it warps, and for travelers bound for Andromeda, it transforms the journey into something far more profound than a simple voyage across space. It becomes a one-way passage through time itself. The mathematics of time dilation are precise and unforgiving. As a spacecraft accelerates toward light speed, time aboard that vessel begins to slow relative to the universe outside. At 50% light speed, the difference is subtle. At 90%, it becomes pronounced. At 99.9%, it becomes extreme. Imagine a spacecraft capable of sustained acceleration, gradually approaching the speed of light over years of thrust. To the crew aboard, their clocks tick normally. Their hearts beat at regular intervals. They eat, sleep, and dream as they always have. But outside the ship, in the reference frame of Earth and the Milky Way galaxy they are leaving behind, time races forward at an ever-increasing rate. This phenomenon is not theoretical speculation. Particle accelerators demonstrate time dilation daily. Subatomic particles that would normally decay in microseconds survive for far longer when accelerated to near light speed, their internal clocks slowed by the effects of relativity. Atomic clocks flown on aircraft return showing measurable time differences compared to identical clocks left on the ground. The universe has shown us again and again that time is not absolute. It is relative, dependent on velocity and gravity, woven into the very fabric of space-time. For a journey to Andromeda, time dilation creates a paradox so profound it challenges our understanding of what it means to travel at all. If our spacecraft could somehow accelerate to 99.99% of light speed and maintain that velocity, the subjective experience of the crew might compress the journey dramatically. What appears to Earthbound observers as a voyage lasting 2.5 million years could, for the travelers, feel like thousands of years, or with sufficient acceleration, perhaps even less. The faster they travel, the more time compresses aboard the ship. In theory, approaching infinitely close to light speed, though impossible in practice, time dilation could make the journey feel astonishingly brief. But here lies the cruel truth. While the travelers experience shortened time, the universe outside does not. Earth continues its orbit around the Sun. The Sun continues its journey around the galactic center. Civilizations rise and fall. Species evolve and go extinct. By the time the spacecraft reaches Andromeda, even if the crew has aged only a lifetime, Earth has aged millions of years. Everyone the travelers knew, everyone they loved, every trace of the world they departed from, has vanished into deep history. The planet they left behind exists only in memory and in the ancient light that continues spreading outward from Earth's past. Light that may never catch up to travelers moving at near light speed. This is the twin paradox, extended across galactic distances. In the classic thought experiment, one twin travels at relativistic speed while the other remains on Earth. When the traveling twin returns, they have aged far less than their sibling. The paradox resolves when we account for the acceleration and deceleration required to turn around, breaking the symmetry between the two reference frames. But on a journey to Andromeda, there is no return. There is no reunion. There is only departure, a one-way leap not just across space, but through time itself. The travelers become unstuck from their era, moving forward through centuries and millennia, while experiencing only the passage of their own subjective years. Consider the weight of this realization. To embark on such a journey is to accept exile not from a place, but from time. It is to willingly sever all connection to the present, to step outside the timeline shared by everyone and everything you have ever known. The messages sent back to Earth, transmitted at light speed, would take 2.5 million years to arrive. By the time Earth receives news of the travelers' safe arrival in Andromeda, the descendants of those who waved goodbye would be separated by a temporal chasm wider than all of recorded human history, multiplied 100 times over. The philosophical implications spiral outward like ripples in a cosmic pond. What does it mean to travel when the destination exists in a different epoch than the departure? Is it still a journey? Or is it a form of time travel, moving forward into Earth's distant future while experiencing one's own present. The travelers would not witness Earth's future directly. They would simply arrive in Andromeda knowing that if they looked back toward the Milky Way, the light reaching their eyes would be ancient, showing a galaxy as it was millions of years before their arrival. Earth itself might no longer exist. The sun might have expanded into a red giant, consuming the inner planets. Humanity might have spread across the stars, or vanished entirely, or evolved into something unrecognizable. Some physicists have contemplated whether this temporal displacement might actually make intergalactic travel more psychologically bearable. If the subjective journey time could be compressed through time dilation, the crew might experience a voyage measured in decades rather than millions of years. From their perspective, Andromeda would be reachable within a human lifetime. But this comes with an irreversible cost. They would arrive as ambassadors from a vanished age, their knowledge obsolete, their language perhaps archaic or forgotten, their very DNA a museum piece from an evolutionary past. They would be ghosts made flesh, haunting a future they can visit but never truly inhabit. Time dilation also creates practical complications that extend beyond philosophy. Any communication with Earth becomes impossible in real time. The travelers cannot phone home for guidance, cannot receive updated scientific discoveries, cannot learn whether their sacrifice meant anything to the civilization they left behind. They are cosmically alone, moving through a bubble of space-time that flows differently than the rest of the universe. Their isolation is not just spatial, but temporal, a separation measured not in miles, but in epochs. And yet, there is something achingly beautiful in this paradox. Time, dilation reminds us that the universe operates on scales and principles that dwarf human intuition. It reveals that reality is stranger and more intricate than our everyday experience suggests. The same physics that make intergalactic travel so impossibly difficult also hint at the profound interconnection of space, time, matter, and energy. We are not separate from the cosmos. We are woven into it, subject to its laws, shaped by its constants. To journey to Andromeda at relativistic speeds is to embrace a truth both liberating and terrifying. Time is not the rigid framework we imagine. It bends. It flows at different rates. It can be experienced in ways that diverge dramatically, depending on one's path through space-time. The travelers would not escape time. They would simply travel through it along a different trajectory than everything they left behind. They would become temporal nomads, wandering not just between stars, but between moments separated by unimaginable spans. This is the paradox at the heart of relativistic travel. The closer we come to achieving the speeds necessary for intergalactic journeys, the more we transform travel into time displacement. Even if we solve the problems of energy and fuel, even if we build ships that can endure the journey, we cannot escape the fundamental reality that moving through space at such speeds means moving through time in ways that sever us from our origins. The journey to Andromeda is not impossible because of distance alone. It is impossible because it requires travelers willing to leave not just their home, but their entire temporal existence behind, venturing forward into a future where they arrive as relics from a forgotten past. Beyond Saturn, beyond the ice giants, beyond even the scattered objects of the Kuiper Belt and the distant Oort cloud, lies a boundary few contemplate, the edge of our galaxy. And past that edge, stretching toward Andromeda, exists something so profoundly empty that it challenges our very definition of space itself. This is the intergalactic void, a realm where emptiness becomes not just an absence, but a presence of its own. We often think of space as empty, the vacuum between Earth and Mars, the darkness between stars. But these regions are crowded compared to what lies between galaxies. Within our Milky Way, even in the spaces between star systems, there are particles, dust grains, occasional hydrogen atoms, perhaps 1 or 2 per cubic centimeter. Magnetic fields weave through the darkness. Radiation from nearby stars creates a faint but detectable background. There is structure here, invisible threads connecting one stellar neighborhood to another. The intergalactic void is different, profoundly, utterly different. Between the Milky Way and Andromeda stretches a gulf of 2.5 million light-years. In this expanse, the density of matter drops to nearly nothing. Not 1 atom per cubic centimeter, but perhaps 1 atom per cubic meter, or even less, in some regions. The void is not merely empty space, it is the closest thing to absolute nothingness that exists in our universe. No stars to light the way, no nebulae glowing in the distance, no planetary systems to pass, no asteroids to mark your progress. Just darkness so complete that if you looked back at the Milky Way, it would appear as a faint, ghostly spiral, slowly receding into memory. To navigate the intergalactic void is to journey through a place where all familiar reference points dissolve. On Earth, we orient ourselves by landmarks, by the sun's position, by stars in the night sky. Even spacecraft traveling within our solar system use celestial bodies to calculate position and trajectory. But in the void between galaxies, there are no nearby reference points. The stars of the Milky Way would blur together into a single dim glow behind you. Andromeda would remain a barely perceptible smudge ahead, growing imperceptibly brighter over centuries of travel. Navigation here becomes an exercise in faith and mathematics, trusting instruments to hold course across a distance so vast that the smallest deviation could send you thousands of light years off target. And in this emptiness, time takes on a different quality. Years blend into decades, decades into centuries. The isolation is not just physical, but temporal. A spacecraft traversing this void would be cut off from everything humanity has ever known, not just by distance, but by the fundamental speed limit of information itself. Light from Earth, traveling at 186,000 miles per second, would take millions of years to reach a vessel halfway to Andromeda. Any message sent home would arrive long after everyone you knew, everyone they knew, and countless generations beyond them had turned to dust. There would be no emergency assistance, no mission control guiding you through unexpected crises, no possibility of new instructions or updated technology being transmitted. A spacecraft entering the intergalactic void enters it alone, carrying everything it will ever have. Every spare part, every byte of data, every contingency plan must be anticipated before departure. One critical failure, one miscalculation, and there is no rescue. The void offers nothing. No resources to gather, no shelter to seek, no alternative route to consider. The hazards accumulating over such a journey defy easy comprehension. Radiation, cosmic rays streaming through space from distant galaxies and quasars, would bombard the spacecraft continuously. Within our galaxy, stellar magnetic fields and the sun's protective heliosphere provide some shielding. But in the void, there is no protection. Over millions of years, this constant bombardment would degrade materials, corrupt computer systems, damage any biological organisms aboard. Even the most sophisticated shielding would slowly erode, atom by atom, under the relentless assault of high-energy particles. Then there are the micrometeorites, infinitesimally small, but traveling at tremendous velocities. Within the Milky Way, the occasional collision is expected, planned for, but crossing the intergalactic void means exposure for timescales that dwarf anything we've designed spacecraft to endure. A journey of 1,000,000 years means 1,000,000 years of tiny impacts, each one insignificant, but accumulating like grains of sand wearing down a mountain. Hull integrity would gradually degrade, surface materials would pit and scar. Over cosmic time scales, even the most robust engineering becomes fragile. Perhaps more challenging than the physical hazards is what the void does to the mind. We are creatures shaped by context, by relationship to our surroundings. We define ourselves in relation to others, to places, to the passage of recognizable time. But in the intergalactic void, context dissolves. There is no weather, no cycle of seasons, no sunrise to mark the day's beginning. The view from any window would remain essentially unchanged for millennia. The same darkness, the same distant smudges of galactic light, the same absolute silence. Psychologists have studied isolation in extreme environments, Antarctic research stations, submarines, long-duration space missions aboard the International Space Station. All reveal that humans need stimulation, variety, connection. We need to see that our actions have effects, that our journey is progressing. But in the void, progress becomes imperceptible. 1,000 years of travel might move you a fraction of a percent closer to Andromeda. How would the human mind, or even an artificial intelligence, maintain purpose across such scales? Some theorists suggest hibernation or suspended animation as a solution. Sleep through the void, wake when Andromeda's stars begin to resolve into individual points of light. But this assumes technology that can preserve biological or mechanical systems across millions of years without failure, without degradation, without the gradual decay that claims all complex structures given enough time. Others propose generation ships, enclosed worlds where entire civilizations might live and die en route. But even here, the void presents unique challenges. Within a galaxy, even on a generation ship, you could observe your progress against the backdrop of passing star systems, navigational milestones marking your journey. In the void, there are no milestones. Children born aboard such a vessel would grow old and die without seeing any change in the view outside. How do you maintain cultural memory, maintain purpose, when the destination exists only as an abstract concept, never growing visibly closer? The intergalactic void is not just empty space. It is a test of everything we understand about endurance, engineering, and existence itself. It is the ultimate isolation, a place where the universe strips away all comfort, all familiarity, and asks a simple question. Can anything, biological or mechanical, conscious or programmed, truly cross this emptiness and emerge intact on the other side? As we contemplate the journey to Andromeda, it is here, in the void between galaxies, that the impossibility becomes most clear. Not because the physics prevents it, but because the void asks us to endure something that transcends physics. A passage through absolute emptiness, guided only by hope and mathematics, toward a destination that remains forever distant, until suddenly, impossibly, it is near. If we cannot reach Andromeda within a human lifetime, perhaps the answer is not to try. Perhaps the answer is to create a vessel that becomes something more than a spacecraft, something that transforms into a world unto itself, carrying not just travelers, but entire civilizations across the cosmic ocean. This is the concept of the generation ship. A vessel designed not for a single journey, but for countless lifetimes. A floating island of humanity sailing through the darkness, where children are born, live their entire lives, and die without ever touching solid ground, passing the torch of exploration to descendants who will continue a voyage their ancestors began centuries before. The generation ship represents one of humanity's most profound attempts to solve the problem of distance. If we cannot move faster, we extend time. If we cannot compress the journey, we accept its duration and design for permanence. In theory, such a ship would be enormous, perhaps miles long, rotating to create artificial gravity, housing ecosystems, farms, forests, and cities within its hull. It would be self-sustaining, recycling air, water, and waste with perfect efficiency. It would carry libraries containing all human knowledge, genetic repositories preserving Earth's biodiversity, and populations large enough to maintain genetic diversity across thousands of years. On paper, the mathematics seems possible, but in practice, the generation ship confronts challenges that go far beyond engineering. The biological reality is the first obstacle we encounter. A viable human population requires genetic diversity to prevent the catastrophic effects of inbreeding. Population geneticists estimate that a minimum of several thousand individuals would be necessary to maintain healthy genetic variation across hundreds or thousands of generations. But even with careful planning, genetic drift becomes inevitable. Random mutations accumulate. Certain traits become dominant purely by chance. Over millennia, the descendants aboard the ship might evolve in subtle ways, adapting to artificial gravity, recycled air, and the unique radiation environment of deep space. They would no longer be quite the same species that departed Earth. The humans who arrive at Andromeda, if they arrive at all, might be fundamentally different from those who began the journey. And this raises questions we have never had to answer before. What does it mean to be human when the environment that shaped us, Earth's gravity, its atmosphere, its sunlight, no longer exists? When generations pass who've never seen a horizon, never felt rain, never walked on ground that was not metal and machinery, the generation ship does not just carry people. It carries the very definition of what humanity might become. Beyond genetics lies an even more complex challenge: the preservation of social stability across timescales that exceed any civilization in human history. The longest continuous civilization on Earth, depending on definition, spans perhaps 5,000 years. A journey to Andromeda would require at least 2.5 million years, even travelling at near light speed, which remains far beyond our technological capability. More realistic estimates, using propulsion systems we might actually develop, push the journey to tens of millions of years. Across such timescales, how does a society maintain its purpose? How do you convince generation after generation to honour a mission they did not choose, to sacrifice their lives for a destination they will never see, based on the dreams of ancestors so distant they become mythology? History suggests that societies transform, fragment, and reinvent themselves constantly. Languages evolve into mutual unintelligibility within centuries. Political systems collapse and reform. Religions rise and fade. Aboard a generation ship, cut off from external influence, isolated in the absolute void between galaxies. Social evolution might accelerate or stagnate in unpredictable ways. Factions could emerge, philosophies could diverge, and conflicts could erupt over resources, governance, or the fundamental question of whether to continue the journey at all. What happens when a generation decides the mission is meaningless? When they choose to stop, to turn back, or simply to drift, transforming the ship into a permanent nomadic habitat with no destination. There would be no authority capable of intervening, no outside force to correct the course. The ship becomes its own isolated universe, subject to forces of change that cannot be predicted or controlled. Equally troubling is the problem of technological drift and knowledge preservation. A generation ship must maintain incredibly complex systems across millennia: propulsion, life support, navigation, communication, all functioning without failure for timescales far beyond the designed lifespan of any technology humans have ever built. This requires not just redundancy, but the continuous transmission of technical knowledge from generation to generation. Every child born aboard the ship must be educated to understand systems they rely upon, but did not create. But education systems degrade, languages shift, priorities change. There is a very real possibility that over thousands of years, the descendants aboard the ship might lose the technical understanding necessary to maintain their own vessel. What was once engineering becomes ritual. What was once science becomes mythology. Instructions for repairing critical systems might be followed not because they are understood, but because they are tradition, passed down as religious commandments, their original meaning lost to time. We have seen this happen on Earth. Ancient technologies, lost to subsequent generations, knowledge erased by war, disaster, or simple neglect. On a generation ship, there is no archaeological record to rediscover. There are no ruins to excavate. If knowledge is lost, it may be irretrievable, and the consequences would be catastrophic. A single critical system failure, centuries into the journey, could doom everyone aboard. Not because the problem is unsolvable, but because no one remembers how to solve it. And beneath all these practical concerns lies an ethical question that cannot be ignored. Is it morally justifiable to condemn thousands of generations to life aboard a spacecraft, to be born into a mission they did not choose, to live their entire existence in service of a goal they may not value? The first generation volunteers. They choose the journey, but their children do not choose, nor do their children's children. Each successive generation is born into circumstances determined entirely by the decisions of ancestors they never knew, trapped in a metal world, hurtling through darkness toward a destination that remains forever theoretical, forever beyond their reach. What right do we have to impose such a fate? Some argue that this is no different from the circumstances of birth itself. No one chooses to be born. No one chooses the world they inherit. But there is a profound difference between inheriting Earth, a world of vast possibility, and inheriting a spaceship, a world of absolute limitation. The descendants aboard a generation ship would live lives defined entirely by containment, by walls that can never be crossed, by horizons that can never expand. For them, the universe beyond the hull becomes not a destination, but a prison they can never escape. Yet even if we could solve every one of these challenges, even if we could design a perfect generation ship with flawless technology, stable society, and willing participants across countless generations, the ultimate truth remains. For journeys between galaxies, even generation ships are not enough. The distances are simply too vast. To reach Andromeda, even a generation ship traveling at a significant fraction of light speed would require millions of years. The ship itself would age. Metal fatigues. Materials degrade. Cosmic radiation slowly erodes structural integrity. No vessel, no matter how well designed, can function indefinitely. Entropy is not negotiable. The generation ship is a beautiful idea, a testament to human optimism and ingenuity. But it is an idea that works only within the scale of a single galaxy. Beyond that, even the longest journey has an ending not in arrival, but in the slow, inevitable decay of time itself. We are forced to confront a truth both humbling and profound. Some distances are not measured in miles or years, but in the limits of what life, any life, can endure. The farther we drift from the comforting gravity of our own galaxy, the more a quiet question begins to whisper at the edge of thought. Is there a shortcut we're missing? A hidden door carved into the fabric of reality itself? Because if crossing the gulf to Andromeda by conventional means takes longer than stars stay lit, perhaps the problem is not our ambition, but our method. Here, our journey leaves the realm of engines and fuel tanks and steps into a stranger landscape, the geometry of space-time. In this region, distance is not only something you cross, it is something you might, in principle, bend. Physicists once imagined space as a passive stage, an empty backdrop on which matter and energy perform. But Einstein revealed that space is not the stage. It is part of the performance. Mass and energy tell space-time how to curve, and that curvature tells matter how to move. Gravity is not a force reaching out across a void. It is the shape of the void itself. If space can bend around stars and galaxies, could it also bend in ways that help us? Could we sculpt a path where Andromeda is not 2.5 million light-years away, but just around a cosmic corner? One of the boldest attempts to answer that question came in 1994 from a physicist named Miguel Alcubierre. Instead of asking, how do we move a ship faster, he asked something more radical. What if the ship does not move at all? In Alcubierre's solution to Einstein's equations, the spacecraft sits inside a bubble of flat space-time. Ahead of the bubble, space itself contracts. Behind the bubble, space expands. The ship never breaks the speed of light within its local region, yet the bubble can ride a wave of expanding and contracting space-time, effectively carrying the ship across the universe faster than light could travel in normal unwarped space. From inside, there is no sense of acceleration, no crushing G-forces. Stars would appear to glide past at impossible speeds, while the clocks aboard the ship tick calmly forward. To an outside observer, the bubble seems to outrun light itself. To the ship, nothing forbidden has happened. It has simply let space-time do the travelling. In the language of science fiction, this is a warp drive. But the universe does not grant shortcuts so easily. The equations that describe the Alcubierre drive demand something we have never seen: exotic matter with negative energy density. In our everyday experience, energy is positive. It fills, it fuels, it heats, it moves. Negative energy density is different. It is not just cold or empty. It is a kind of anti-weight in the fabric of space-time, where positive energy curves space inward, like a ball sinking into a mattress. Negative energy would pull space up, creating a rise instead of a dent. To contract space in front of the ship and expand it behind, the warp bubble must be threaded and braced with this strange, repulsive ingredient. there are hints that the universe allows negative energy in tiny, fleeting amounts. In quantum physics, empty space is not truly empty. Particles and antiparticles flicker into existence and then annihilate again in unimaginably brief moments. In certain configurations, these quantum fluctuations can lead to regions where the measured energy dips below what we call zero. The Casimir effect, observed between two closely spaced metal plates, is an example where the vacuum itself behaves oddly, as if it carries a slightly negative pressure. But these effects are microscopic and delicate, more like ripples in a pond than the roaring ocean we would need. The original Alcubierre calculation suggested energy requirements greater than the mass of the observable universe, all arranged in a configuration of negative density that we have no idea how to engineer or sustain. Later, refinements have dramatically reduced the theoretical energy cost on paper. Yet even the more modest versions demand a form of matter that current physics does not know how to create, bottle, or control in macroscopic quantities. Warp drives are not alone in asking for such miracles. Another theoretical shortcut rises from general relativity, like an archway between distant realms, the wormhole. In the equations, a wormhole is a tunnel that connects two separate locations in space-time. Imagine folding a sheet of paper so that two distant dots touch. Pierce the paper with a pencil, and you have made a bridge. On the cosmic scale, a wormhole would do something similar. Instead of traveling across the map of the universe, you dive through it. In principle, a traversable wormhole could turn the journey from the Milky Way to Andromeda from millions of years into minutes or even seconds. On one side, our familiar spiral of stars. On the other, Andromeda's luminous disk hanging in the alien sky. The distance in normal space remains vast, but the path through curved spacetime is short. However, the same physics that allows wormholes also conspires against them. A natural wormhole, if it forms at all, appears to be unstable. Under its own gravity, the tunnel throat pinches closed at nearly the speed of light, snapping shut before anything larger than a photon can pass through. To hold the wormhole open, something must prop the tunnel against collapse. Once again, the equations point to exotic matter with negative energy density. Threads of this strange substance, arranged along the throat of the wormhole, would act as scaffolding against gravitational collapse, creating a stable passage through which a spacecraft might travel. Remove the exotic matter and the tunnel pinches off. Even if such a structure could exist, the challenges do not end there. Quantum effects near the wormhole mouth may generate intense radiation. Tidal forces could become enormous as space-time curves sharply around the throat. The smallest error in configuration or stability could turn the gateway into a gravitational shredder. These are not just engineering problems. They are invitations to new forms of catastrophic failure that we do not yet fully understand. Warp drives and wormholes share a deeper issue. They are solutions to equations, not designs for machines. In mathematics, many things are possible that the physical universe never builds. A bridge can exist perfectly on paper across any chasm. That does not mean the materials in our world can support it. The distinction between mathematical possibility and physical reality is subtle but crucial. In general relativity, you can write down many exotic spacetimes, rotating universes, time machines, warp bubbles, wormholes. But to move from chalkboard to cosmos, every curve in spacetime must be sourced by actual matter and energy that obey the fundamental rules of our universe: conservation laws, quantum field behavior, thermodynamics, causality. At the moment, every serious attempt to examine these theoretical shortcuts runs into the same wall. They require forms of matter we have never observed, in quantities and arrangements that may be forbidden by deeper principles of physics we are only beginning to glimpse. Quantum inequalities seem to limit how much negative energy can exist, and for how long. Feedback effects may destabilize warp bubbles or wormholes as soon as they form. The same quantum fields that allow a tiny Casimir effect may tear apart any attempt to scale that trick up to intergalactic sizes. This does not mean these ideas are foolish. It means they are frontier markers, signposts at the edge of what our current theories can describe. They tell us that if space-time shortcuts are possible, they will demand a level of understanding that reaches beyond both our technology and, quite possibly, our present-day physics. In science fiction, the transition from idea to implementation is as simple as throwing a switch. Engage. In our universe, the distance between an equation and an engine is as daunting as the distance between galaxies themselves. For now, the consensus among most physicists is cautious. Warp drives and traversable wormholes remain, with our current knowledge, in the realm of speculation. They are mathematically intriguing, conceptually beautiful, and profoundly useful as thought experiments. They help us probe where relativity and quantum theory might clash, and where new physics may be waiting. But as tools for actually reaching Andromeda, they are no more real today than the wooden wings of early dreamers were to crossing the Atlantic in a single night. As we drift onward through the dark, it is tempting to see this as a disappointment, a door closed. Yet there is another way to view it. Every impossibility we encounter is also a question. Why does the universe resist these shortcuts? What does that resistance reveal about the deep architecture of reality? In the silence, between galaxies, our most powerful engines may not be rockets or warp drives, but questions themselves. And the answers they seek will lead us, inevitably, to another barrier. One not built of distance or fuel, but of the universe's own expansion. A boundary written not in metal or matter, but in the restless push of dark energy, stretching space faster than our dreams can chase it. The deeper we travel into the dark, the more a quiet realization begins to form. Rockets, fuel, speed, even human lifetimes, these were our first obstacles. They felt enormous, unconquerable. But out here, beyond the glow of familiar stars, we begin to sense something else. A barrier not made of metal or distance or biology, but of the universe itself. Space is not just a backdrop for our journey. It is an active participant. For most of human history, we imagine the cosmos as still. The stars were lanterns hung in a fixed, eternal sky. Even when we learned that galaxies were separate island universes drifting in the dark, we thought of them as sailing slowly through a static ocean. But the ocean itself is moving. Roughly 100 years ago, astronomers like Edwin Hubble began to notice something strange. The light from distant galaxies was stretched, shifted toward the red end of the spectrum. It was as if the fabric of space between us and them were being pulled taut. The further away a galaxy was, the more its light was stretched. From this, a profound truth emerged. The universe is expanding, not like an explosion from a central point where fragments fling outward into empty space, but more like the surface of a rising loaf of bread. The galaxies are the raisins. They aren't racing away through space. The dough, the space itself, is swelling, carrying everything with it. From any raisin's point of view, all the others seem to rush away. This expansion alone would already complicate our dream of reaching another galaxy. Because when you're trying to cross a gulf that is literally growing while you travel, even fast enough is a moving target. Imagine trying to swim to an island while the ocean between you and the shore stretches wider with every stroke. But expansion, by itself, is not the final problem. For a long time, scientists thought the expansion might slow down. Gravity, pulling on every star and galaxy, was expected to gradually tug the universe back, like a ball thrown upward that must eventually yield to the pull of Earth. Some even wondered if the cosmos might someday stop expanding and fall back into a big crunch. Then, in the late 1990s, astronomers measuring distant supernovae discovered something unsettling. The universe was not slowing down, it was speeding up. Galaxies weren't just drifting apart, they were being pushed apart, faster and faster by something unseen. A kind of energy woven into the very vacuum of space. Not like the energy stored in fuel or light or motion, but a subtle pressure that exists everywhere, always, growing in total power as space itself grows. We gave it a tentative name, almost a placeholder for our ignorance: dark energy. We don't know exactly what dark energy is. It does not glow or burn or collide. We infer its presence from its effects, like feeling the wind without seeing the air. It appears to make up about 70% of the total energy content of the universe, quietly guiding its fate. And its main effect, for anyone dreaming of visiting Andromeda or anything beyond, is simple and devastating. It turns the expansion of the universe into an ever-accelerating escape. As dark energy pushes space to expand faster, the distances between most galaxies grow at an increasing rate. Not because galaxies are firing thrusters, but because there is more and more space being created between them. This creates a strange, almost paradoxical situation. You could build a spacecraft that moves at an enormous fraction of the speed of light, perhaps even skim the cosmic speed limit itself. You could point it toward a distant galaxy, lock in your course, and fire every engine you have. And yet, for many galaxies, you would never arrive. Not because you are too slow, but because the space between you and your destination expands so quickly that even light, nature's fastest messenger, cannot bridge the gap. The galaxy's light will reach you now, from the past, carrying the story of what it once was. But any light or ship you send back in reply will never catch up. This is the concept of the cosmic horizon. Just as Earth's curvature hides ships beyond a certain distance at sea, the accelerating expansion of space hides regions of the universe behind a kind of dynamic, invisible boundary. Beyond that horizon, galaxies recede from us faster than light, not because they are breaking relativity's laws, but because the space between us and them expands too rapidly. We can see some of these galaxies today because their light left billions of years ago, when they were still closer, when the cosmic expansion was gentler. But as time goes on, more and more of the universe will slip beyond this horizon, not disappearing, but becoming permanently unreachable. This is not science fiction. It is one of the best supported predictions of modern cosmology. In that far, dim future, the night sky will grow emptier, star by star, galaxy by galaxy. The cosmic web of shimmering clusters that we see in today's telescopes will fade from view. The relic light of the Big Bang itself, the cosmic microwave background, will stretch so thin to such long wavelengths that it will become practically undetectable. To the inhabitants of that era, if any exist, the universe will not look like an expanding cosmos born in a fiery beginning. It will look like a cold black void surrounding a single island of matter, their own galaxy. And here lies a quiet twist in our story. We live in a very special neighborhood. The Milky Way and Andromeda are not being pulled apart by dark energy. Instead, they are bound together by something stronger on local scales: gravity. Despite the universe's global expansion, our two galaxies are on a collision course, slowly falling toward each other at about 110 kilometers per second. In about 4 to 5 billion years, roughly when our sun is beginning to swell into a red giant, Andromeda and the Milky Way will collide, not like two solid objects smashing together, but like immense ghostly spirals passing through each other, their stars mostly slipping past in the vast emptiness, while their gas clouds compress, ignite, and form new stars in titanic waves. Over billions of years, they will merge into a single giant elliptical galaxy, often nicknamed Milkdromeda or Milkomeda. Our night sky, if anyone is still there to see it, will be totally transformed. Great arcs of stars will stretch overhead. Tidal streams of light will crisscross the heavens. The combined core will glow like a distant, brilliant ember. From the standpoint of intergalactic travel, this future merger is an opportunity. You would not need to cross a gulf between galaxies if, given enough time, the galaxies themselves come together. Planets, star systems, perhaps even civilizations, once separated by millions of light years, could find themselves in the same galactic city. But beyond that city, darkness. Because while the Milky Way and Andromeda are falling inward, most other galaxies are being carried away by the expansion of the universe, accelerated by dark energy. The local group of galaxies, our small cosmic neighborhood, consisting of the Milky Way, Andromeda, and a few dozen dwarfs, will collapse into a single bound structure. Everything else will recede. Trillions of years from now, after countless orbits, collisions, and stellar deaths, this merged galaxy will be adrift in a universe that has grown unimaginably vast and silent. No new galaxies will fall in. No fresh starlight from beyond will arrive. Dark energy will have pushed the rest of the cosmos over the horizon, locking them away beyond reach, beyond even information. In that deep future, the idea of traveling to another galaxy will not just be difficult, it will be meaningless. There will be no other galaxies in sight, no Andromeda glowing faintly across the void as a challenge to our ambition. Only the great solitary island of merged starlight, surrounded by a blackness that hides everything else. This is the ultimate barrier. Not a wall we can break with better engines, but a change in the universe's behavior itself. A shifting of the cosmic stage in which our entire drama takes place. Even today, at our young cosmic age of about 13.8 billion years, we are already living in a universe where most galaxies are forever beyond reach. In the observable cosmos, there are perhaps 2 trillion galaxies, but only a tiny fraction of them, those within our local gravitational neighborhood, are even potentially accessible in principle. Andromeda is one of the lucky few, not just visible, but bound to us by fate. When we dream of going there, We are already focusing on one of the only destinations that the universe has not yet placed behind a one-way horizon. In a sense, our impossible journey is aimed at a moving target that is drifting, slowly, inevitably, not away from us, but toward us. Yet even that doesn't rescue the dream, because while the universe gives us this one small gift, a future collision rather than eternal separation, it takes away something larger. It turns the rest of the cosmos into a landscape that is not just distant, but fundamentally isolating in the long run. We often think of space as empty, but on human timescales, it is crowded with possibilities. Thousands of exoplanets, billions of stars in our galaxy, trillions of galaxies beyond. A cosmic city glittering in every direction. Dark energy whispers a different story. A slow, patient unraveling. Galactic clusters that are now tenuously bound will someday separate, each cluster becoming its own island, then its own lone beacon. The pathways between them, once merely long, will become non-existent, erased not by destruction, but by expansion. Imagine a civilization that arises in the far future, long after the merger of the Milky Way and Andromeda. To them, the sky holds only their own galaxy. No cosmic background radiation, no distant galaxies, no redshift to measure, no clues to an expanding universe, a big bang or a cosmic web. They might conclude that their galaxy is the entire universe, that the stars around them are all that ever were, all that ever will be. The grand story we have pieced together, with telescopes, equations, and fragile ingenuity, will be unavailable to them, hidden by the very laws that gave rise to it. The irony is delicate and profound. We live at a time when the universe is just transparent enough to reveal its vastness, but not yet so old that most of it has slipped away. We are early enough to see the grand architecture, but late enough to recognize that it is already dissolving. In this light, the impossibility of reaching Andromeda is not just an engineering problem. It is a reminder that we are small participants in a cosmic drama that cares nothing for our timelines. We imagine building ever faster ships, harnessing exotic physics, even bending space-time itself. But dark energy tells us that there are horizons that no technology can cross. Boundaries written not in metal or willpower, but in the fundamental structure of reality. The universe is opening and closing doors on timescales so vast, our language barely reaches them. For now, Andromeda shines in our night sky as a faint smudge, a neighboring island across a dark sea. It is both impossibly distant and inevitably close, unreachable today, yet destined to collide with us long after we are gone. Beyond it lie galaxies we will never visit, stars whose light will never reach our descendants, civilizations, if they exist, cut off from us forever, not by malice or war, but by the quiet, relentless stretching of space. And in that stretching, in that slow, accelerating drift, there is a kind of cosmic loneliness. Not the loneliness of being alone, but of knowing that connection itself has limits. That even if life blooms in countless places, most of those lights will pass each other like ships in a fog, seen from afar for a brief moment of cosmic time, and then lost behind horizons no traveller can cross. We set out to reach Andromeda and discovered instead that the universe is not simply large. It is changing beneath our feet. The ultimate barrier is not distance, it is time. It is the way the universe chooses to evolve. And as we stare across the void, watching Andromeda's faint glow, we are left with a question that reaches beyond physics. What does it mean to be part of a cosmos where some dreams are not just difficult, but written out of the script by the universe itself. The farther we travel in thought, the more a quiet realization settles over us. We are not going to Andromeda, not in a human lifetime, not in 100, not with any technology that resembles ships, rockets, or reactors. The numbers we've traced are not just large. They are verdicts. They whisper a simple, unsettling truth. We are confined to our local galactic neighborhood. The Milky Way is no longer just a starry band painted across the night. It is our island, our continent, our entire accessible world carved out by the laws of physics. For a species that once believed the horizon was the end of everything, this is both familiar and strange. We have always lived inside boundaries we did not understand. Now we begin to see the outline of the final one. In the same way that the asteroid belt felt like an unfinished sentence, our relationship with the wider universe becomes a story we may never physically complete. Andromeda hangs in the sky as a silent promise we are not allowed to collect. At least, not as we are now. For some, this feels like a cage. We are used to telling ourselves a particular kind of story, that progress is a straight line, that every frontier eventually falls, that there is no door the human mind cannot find a way to open. Steamships conquered oceans, aircraft conquered skies, rockets reached the moon. So it is tempting to assume that Andromeda is simply the next chapter, delayed but inevitable. Yet when we listen more carefully to the universe, it answers with a different tone. Not a taunt, not a refusal, but a boundary, a speed limit, a horizon that recedes faster than we can chase it. Beyond a certain scale, ingenuity alone is no longer enough. We are not being denied by a lack of imagination, but by the shape of space-time itself. This is the humbling reality of cosmic limits. Humility in science is not defeat. It is orientation, a way of turning to face the truth without turning away from wonder. The same equations that tell us Andromeda is out of reach also tell us how stars live and die, how galaxies spin, how time curls around mass. They are not walls put up to keep us small. They are the blueprint of everything that exists. From that blueprint emerges a strange kind of comfort. If we cannot escape the Milky Way, then the Milky Way is not our prison. It is our home. This realization begins to reshape our perspective. For centuries, we imagined humanity as climbing a ladder: village, continent, planet, star system, galaxy, universe. Each rung to be claimed, each level to be mastered. But maybe the universe is not a ladder. Maybe it is an ocean, and we are a coastal species learning to sail. We will never drink the entire sea. We will never walk every shore. Yet the parts we do reach are no less real, no less meaningful, because of the vastness that remains untouched. If anything, our confinement amplifies the value of what is near. Our local cosmic environment, this modest corner of a spiral arm, this collection of stars, planets, and drifting ice, is not generic background. It is the only stage, as far as we know, where life has begun to ask questions about itself. The sun is not just another star, it is our star. Jupiter is not just a gas giant, it is our ancient guardian, deflecting comets that might have ended our story before it began. The asteroid belt is not just rubble, it is the scattered archive of our system's formation. Even the empty space between stars is not truly empty. It is threaded with magnetic fields, dust, and the faint echo of long-dead supernovas that forged the atoms in our blood. We live in a neighborhood that has been preparing for our arrival for billions of years, without knowing we were coming. To understand that Andromeda is unreachable is also to understand how precious this neighborhood really is. There is another shift that happens when we accept cosmic limits. Our obsession with destinations begins to loosen. When you cannot ever arrive, the question changes. What does it mean to travel? We imagine a ship launched toward Andromeda, knowing it will never get there. Generation after generation lives and dies between the stars. Their entire civilization unfolding inside a vessel that will only ever cross a fraction of the gulf. At first, this seems tragic, almost cruel, a journey with no arrival. But when we look more closely, something else emerges. All meaningful journeys have this quality. Our species will never reach an endpoint called complete understanding. No individual life arrives at a final place called finished. Planets do not arrive at permanent stability. Stars do not lock into eternal shine. Everything is in motion, always halfway between where it began and where it will eventually dissolve. Perhaps Andromeda is simply the universe making this pattern visible on a grander scale. It is the unreachable city on the far shore, the lighthouse whose beam we can see but never touch. It reminds us that not every story needs a conclusion to be worth telling. The value may lie in the act of moving, of learning, of building against the dark, not in crossing some ultimate finish line. In that sense, the impossibility of reaching Andromeda is not a failure of ambition. It is an invitation to reconsider what ambition means. Instead of asking, "How do we own the universe?" we might ask, "How well can we know the part we inhabit?" Instead of dreaming only of escape, we can dream of depth. Depth of understanding, depth of care, depth of presence in the thin shell of habitable space that clings to our small blue world and perhaps, someday, to a few others nearby. This does not mean giving up on exploration. Quite the opposite. Within our own galaxy, there are hundreds of billions of stars, many with planets, some with oceans, some perhaps with minds looking back. The Milky Way is not a consolation prize, it is a cosmos in its own right. We may never reach Andromeda, but we can still map our own spiral arms, wander the silent gulfs between clusters, listen for radio whispers from civilizations that rose and fell long before we walked upright. We can send instruments to the icy moons where alien oceans slosh in the dark. We can float cities in the skies of gas giants, mine asteroids, terraform worlds, build habitats that drift between stars like dandelion seeds on a galactic wind. Within the limits the universe sets, there is still an almost unbearable abundance of possibility. And there is one more, quieter implication. If this galaxy is likely the only one we will ever touch, then what we do here matters on a scale we rarely acknowledge. Our choices are no longer just human decisions. They are galactic events. The moment a technological civilization appears in a spiral arm, it changes that arm forever. It alters the future distribution of matter, the pattern of signals, the way energy is used and transformed. In a universe where most galaxies will never meet, each one becomes the sole stage for its own unfolding dramas. In the Milky Way, we might be one of the first acts, or one of the last, or one of many, separated by distances so vast that even light will never carry our stories to each other before the stars burn out. We do not know, and that uncertainty is not emptiness, it is possibility, a space for meaning to grow. Our cosmic limitations do not tell us what to value, they only tell us that whatever we choose to value, we must do it here. Within this finite span of time, within this single river of stars, We cannot outsource our responsibility to some future, omnipotent version of ourselves that will fix everything once we reach other galaxies. We will not reach them. The work of becoming who we wish to be will happen here, or it will not happen at all. That might be the most profound implication of all. The impossibility of Andromeda is a mirror held up to our own planet. It asks, gently but firmly, if this is all you ever have, this sky, this star, this fragile biosphere, this brief moment between ice ages, what will you make of it? How will you treat it? How will you treat each other? In the end, the universe does not owe us infinite horizons. It offers us something else. A single extraordinary window of time in a single extraordinary place, bounded by laws that are harsh but comprehensible, unforgiving but consistent. Within those bounds, meaning is not given. It is built. Perhaps humanity's future is not defined by how far we go, but by how deeply we learn to live inside the distance we are given. We have come a long way without ever leaving our own cosmic backyard. From the restless storms of Jupiter to the fragile rings of Saturn, from the thin breath of interplanetary space to the thick silence between galaxies, each step of this thought journey has revealed a new layer of impossible. The first layer is distance. Andromeda hangs in our sky as a soft, hazy smudge. To the naked eye, it seems almost close, as if you could reach out and brush it with your hand. Yet that faint blur is an island of 1 trillion stars, more than 2.5 million light-years away. Even at the speed of light, a beam racing through space would take longer than the entire history of Homo sapiens just to arrive. Distance at this scale is not a number. It is a wall made of time. Then comes speed. We have learned how to fall around planets, how to steal momentum from Jupiter, how to ride gravity as if it were an invisible engine. We have built machines that escape the solar system entirely, but compared to light, even our fastest probes drift like dust motes in a cathedral. Relativity does not merely advise us to slow down. It enforces a speed limit built into the structure of reality itself. To push close to that limit demands energy so vast it begins to rival the output of stars. And the energy problem is its own impossibility. To carry the fuel needed to accelerate a starship to a meaningful fraction of light speed, then slow down again near Andromeda, means launching not a ship, but a moving mountain of reaction mass. Each kilogram of fuel makes the ship heavier, which demands more fuel, which makes it heavier still. It is an exponential trap, a spiral of requirements that seems, with our current understanding, to have no practical escape. Time folds in on itself as we go faster. At relativistic speeds, the clocks aboard a hypothetical ship would tick more slowly than those left behind. To the travelers, Andromeda might become less impossibly distant. Years could compress into something a single lifetime can hold. Yet in doing so, they would leap forward through the history of the universe. Galaxies would rotate. Stars would be born and die. Civilizations, if they exist, might rise and vanish while a crew sleeps between suns. Time dilation turns the impossible journey into a one-way trip into someone else's far future. Beyond all of this lies the most elusive barrier, the expansion of the universe itself. Dark energy, the quiet pressure that accelerates this expansion, is slowly increasing the distance between the largest structures in the cosmos. Some galaxies are already receding from us faster than light, not by breaking the speed limit, but because space between us and them is stretching. One day, far in the future, many of the galaxies we see now will slip beyond a cosmological horizon, forever unreachable, even in principle. The universe is not just vast, it is moving the goalposts as we watch. And yet, in the dome of our night sky, Andromeda remains. A soft, persistent reminder of everything we cannot do. We cannot build a rocket that outruns cosmic expansion. We cannot step from one galaxy to another as easily as from one planet to the next. But we can look. And in that act of looking, something remarkable happens. Andromeda's light is ancient. The photons that touch your eyes tonight began their journey before humans built cities, before our species even knew the stars were other suns. We cannot go to them, but they come to us, carrying messages written in their color, their brightness, their subtle shifts. From this distant glow, we have learned the galaxy's mass, its spin, its impending collision course with our own Milky Way billions of years from now. Observation becomes a kind of contact, not of bodies, but of understanding. Our true story, at least for now, is written closer to home, in the Milky Way, in the local group of galaxies bound together by gravity, in the quiet war between expansion and attraction unfolding right above our heads. We may never plant a flag on a world in Andromeda, but we may uncover oceans beneath the ice of Europa, or clouds rich with complex chemistry on Titan, or traces of ancient life on Mars. The frontier does not end because Andromeda is out of reach. It simply shifts focus, sharpening from the unattainable to the astonishingly near. There is a strange, almost paradoxical beauty in an unreachable galaxy. It reminds us that the universe is not designed to fit within our expectations or our lifespans. It is older, larger, and stranger than any destination we can name. Our role, at least in this moment of cosmic time, is not to conquer that immensity, but to witness it, to measure it, to be the brief, thinking flicker that notices. If you've traveled with this video all the way to this distant horizon, you are part of that flicker. You've carried your curiosity across millions of light years in imagination alone. If this journey gave you something to think about, take a moment to gently support it. Tap like so YouTube knows this kind of content matters, and subscribe so you don't miss the next step into the dark. In the comments, share where you're listening from, your city, your country, or just under the same sky. It's a quiet way to map our own tiny civilization against the canvas of the cosmos, a constellation of humans checking in from one small planet. And if you'd like to go one step further, there is an optional channel membership available. It's never expected, but always deeply appreciated. Members help keep these long, slow journeys through space and time sustainable, and in return, you'll find a few extra things waiting for you behind the scenes. Andromeda may be forever beyond our reach, but the act of wondering about it is not. As you drift towards sleep, remember, some destinations are meant not to be visited, but to be dreamed about. In their beautiful impossibility, they give shape to our questions, our science, and our sense of place in a universe too vast to ever fully hold, yet small enough to fit for a while inside a single human mind.